There's some new results that have come out. Well, they're not that new. They're 2024, 2025. And they're causing a lot of stir because they basically say, wait a second, something's going on with dark energy. And if these results are true, it kind of upends a lot of what we thought dark energy was, what it is, what it says about the reality, about our reality, particularly as it relates to, the space-time. So you have cosmologists that are looking out into space, they're looking at stars, they're looking at galaxies, they do what they do. And part of that is basically understanding this thing called dark energy. Let's go ahead and define what that is, make sure that you understand. Then I'll explain how these new results that are coming from this baryon acoustic oscillation instrument is saying something about dark energy that kind of upends the whole thing and says, wait a second, maybe we got dark energy all wrong. The reason why it's kind of interesting is that, dark energy is supposedly like 70% of everything around us. It's like 70% of our reality, at least according to physicists, according to specifically cosmologists. So you've got 5%, which is the matter that we know, the atoms that we touch, the things that we see here. Then you got 25%, which is dark matter. And then you've got the rest, the 70%, just by bookkeeping, that basically is called dark energy. Now, I'm going to argue in this episode that these new results that are coming out and kind of upending our so-called theory of what dark energy is, it's not as surprising and as career pivoting as it may seem to, the way it's kind of getting talked about in popular science for sure, but even the way some physicists are talking about it. And the reason is because dark energy is quite frankly not much of a theory to begin with. It's already just this placeholder that we have. Now, I get it. There's models and there's math and there's reasons to believe and there's observations. But like a number of other theories, there's kind of a breed of theory in science where it's more placeholder than reality. I'm going to give you some other examples later. And because of that, when some new result comes out and says, oh, it's going to upend our understanding of, well, you didn't really have much of an understanding to begin with, quite frankly, right? So dark energy is this thing that was kind of discovered by subtraction. So you look at things like the CMB, the cosmic microwave background, and you look at the densities of matter, of stars, of whatever's in the universe, and you kind of add it all up, and then you say, wait a second, there's something missing. Like if we look at the density of this cosmic microwave background, which is coming from the Big Bang, it's like this kind of heat signature footprint that's kind of left over from the Big Bang, and you look at it and you can understand and infer a lot of things from it. One of it is like kind of how much matter, I guess you could say, is supposed to be in the universe. And you add it all up and it's like way more than what we see. What we see is like 5%, what we see being the regular matter. And so there's this kind of bookkeeping that goes on, say like 95%, we don't even know what it is, where is it? So then you've got kind of dark matter that comes into that. That's not the dark energy we'll be talking about. Dark matter, which is another essentially placeholder, that's been around, really theorized since the 30s. If you start looking at the rotation, speed, velocity of galaxies, they look like they're spinning too fast, and there's not enough mass of regular matter to explain how that happens. And so you kind of say, well, maybe there's extra mass in there to get the spinning as fast as it is, and we're going to call that mass dark matter. Now, again, I'm kind of downplaying it, and making it sound as though people are just coming up with these theories kind of randomly. Of course, that's not true. There's a reason to believe in dark matter. There's all kind of modeling there. There's mathematics that support the calculations, but still, just by the name, right? Dark matter. It's a bit funny, right? Because it's obviously put there as a stopgap, right? Yes, there's math. Yes, there's models, but we don't really know what it's not giving off light. It doesn't have the properties that normal matter has. It's obviously not something we experience directly as far, so dark matter. So that's 30%. And then the other big gap of 70%, which, in the 80s and most of the 90s, we still didn't know what this was. There's theories about it. Then in 1998, you've got people looking out, you've got the cosmologists looking out in the universe. And not only do they realize the universe is expanding, which they've known for a long time since Hubble, they realize that it actually looks like the universe is accelerating, right? So this kind of was a big thing, obviously. It won the Nobel Prize. This is in 1998. And so the universe isn't just expanding, it's actually accelerating. And I'll get into some of the ways in which they determine that, looking at standard candles and how some of the p-value stuff, which we'll talk about in a bit, overlaps with that. And that's going to kind of put into context what these new results are saying about things like standard candles. But anyway, so the universe is accelerating. And so you had this original thing that Einstein was putting in his equations, kind of as a fudge factor, really, this cosmological constant. And then he ended up calling it his biggest blunder. Apparently, it's more apocryphal. We don't really know. We don't really know if he said that, but he kind of put it in to make the universe act, to make his equations model the universe the way he thought it did, anyways, which is essentially in a static universe, they would call it. And then when they realized the universe was expanding, you had to kind of take it out and say, okay, that's not right. And then when they realized in 1998 that the universe was actually accelerating, then they kind of brought that cosmological constant back in as sort of a quote-unquote explanation for how the actual expansion was accelerating. In other words, it's almost like there's this negative pressure that seems to kind of push, and you got to be careful with the analogies here. Push is not really the right word. I think it's fine for this episode, though. There's this kind of negative pressure that seems to be quote-unquote pushing, right, the universe to go faster and faster. And so that's where this notion of dark energy comes from. And dark energy, again, was already kind of hypothesized, theorized for a few decades. These 1998 studies come out and they're like, oh, well, maybe that's what the dark energy is, right? And so just by subtraction, meaning you do the bookkeeping on all the density from the CME and other things, and you're like, okay, 5% is regular matter. Let's explain the rotation velocities of the galaxies. Okay, that's dark matter. You still got 70% missing. Where is it? Oh, 1998 results come out. The universe is actually accelerating. Okay, that's got to be the missing 70%. Let's call it dark energy. Okay. Now, nobody, it's not much of an explanation, right? It's really just a stopgap. It's right in the name. The fact that you call it dark energy, like, what does that mean, right? Dark, yeah, it doesn't give off light. It doesn't. Really, dark is just meaning unknown. Like, you basically have no idea what this stuff is. And the only kind of mathematical thing, not the only, but the main mathematical thing that you point to, which is the cosmological constant, I mean, you're pointing to math. That's not an explanation, right? It's not the same thing. So, it's not even a model. It's like a constant, right? Okay, so anyways, it makes the math work. So something, negative pressure thing, it seems to be pushing out, quote unquote, pushing the universe to make it accelerate. Okay, so that's been around us for a while now, right? Decades, we get that. And the way that they do that, just to give some background, to know that the universe is actually accelerating and not just expanding. Again, you understand it's expanding because from the Big Bang, it just keeps expanding. It's the acceleration that was really interesting there since 98. They use standard candles. And the basic idea is that, you need to be able to look out at, let's say, galaxies, stars, whatever, and know the distance they are from us, right? From Earth. And how do you do that? That's obviously not, obvious. So what you do is what they came up with is a standard candle, something that gives off a known luminosity, a known amount of light. And then the farther it is from you, the dimmer it would be. So, for example, if I put a 100-watt light bulb in front of your face and then I go a mile away from you and you can kind of see the 100-watt light bulb, assuming, I don't know, a clear sky or whatever, it would be a lot dimmer, right? But because you knew it was 100 watts to begin with, right, you could do different distances. You could look how much the dimness increased or the luminosity decreased, and you would know the distance it is from you. Well, you can do that with supernova, right? Supernovae. And they specifically look at the type 1A supernova. And what that is you basically have this dead white dwarf, and it siphons off material from a companion star, and eventually it gets to some critical kind of limit, 1.4, this kind of Chandrasekhar limit, named after the Indian physicist. Once it gets to the 1.4, it essentially detonates as supernovae do, and it gives off a very standard, well-known, always the same amount of light. So if you look at supernovae and you look out in the universe and you see them go off and you see the light come off, based on how light it is, right, because they always ignite at the 1.4, you know how far away it is. So you can measure distances by looking at supernovae, essentially. And so that's the luminosity side. And then you also have redshift, which is looked at. And this is essentially just the light version of the Doppler effect. So if a motorcycle goes by you and it goes, right, that's because the source of the sound that's propagating the wave is essentially, because it's receding from you, it elongates the wave. Longer wavelength is a lower frequency. So let's say you go from, if it was light, you'd go from blue to red. This would be like a high pitch to a low pitch if you're talking about sound, right? So because the universe is receding from us, right, because it's expanding, you can look at the redshift and you can take into account the distance as well as the stretching, let's say, of space-time that's happening from the redshift. And those come together, and you can realize from those observations that not only is the universe expanding, but it's actually accelerating. So that's what that is. And and p-values would play a role here. I'm going to define p-values in a bit, but we don't worry about that right now. It'll become important later when we talk about the problem of p-hacking, which is one of the suspicions of what might be happening with those new measurements that are coming in, because those new measurements are completely so the new measurements that are coming in are basically saying, wait a second, this idea that the accelerating universe is constant, because that's, since 98 what we've believed, right? Physicists, cosmologists are saying, yes, it's accelerating, but it's essentially a constant acceleration, right? Like things aren't changing. More to the point, it's like the cosmological constant, right, in the name, isn't changing. It's the same. Dark energy is just dark energy. It is what it is. It's like in the vacuum of space, and we don't think it's really a dynamic changing thing. It just is what it is, and it's negative pressure, whatever you want to call that, is causing the acceleration of the universe to occur. Okay. But nothing about dark energy is changing. It's just like a fundamental aspect of the universe. It is what it is. Okay. So now new measurements come out this last couple of years, and they do two things. One, they actually corroborate what was already shown with a lot of that standard candle data, looking at the expansion and more to the point, the acceleration of the universe, meaning it's a completely different physics, right? It's not looking at, the exact same kind of standard candle plus red shifting, whatever. It's actually looking at, well, this is called the baryon acoustic oscillations. We won't get into the physics behind it. Just understand that it's a completely different physics that can look at the same kind of thing. And that's important because it's like an independent corroboration of what that standard candle data in 1998 was doing. And it's basically saying, yeah, you're right. The universe is accelerating. We agree. It's doing what you said it was. But then it's got this other result, which suggests that dark energy itself, or more to the point, the dark energy density is actually shifting. It's changing. Meaning dark energy density is not constant. Okay, so whatever, and again, if you're kind of like, well, yeah, but what is dark energy density? Yeah, that's the point. Nobody really knows. It's kind of this stopgap that has just been put there to try to quote unquote explain why the universe accelerates, right? That's it. I mean, yes, there's math, and yes, there's models, and yes, there's all kinds of other conversation you could put around it, but at the end of the day, it really is a stopgap that you put in there, right? Again, that's why it's called dark energy, right? It's not just, not giving off light. It's just more like unknown, right? You could call it like X energy, like an X-ray. You don't really know, right? Okay, so they don't know, but they've always thought that it was just constant, static, nothing else too much to say about it. Now these new results are coming in, and they're like, no, dark energy itself, the density, whatever it is changing, it's dynamic, and there's all kinds of reasons why the BAO, the baryonic acoustic oscillation, would be able to say that. We don't need to get into that physics. Just understand that it's an independent thing. So it corroborates part of the data, which means, yeah, like the 1998, you're right, you're measuring that. Yes, it's accelerating, but the dark energy density seems to be completely different. Or sorry, it's shifting. It's changing. It's a dynamic thing. Okay, and so now you step back, and this is getting a lot of physicists kind of worked up, and cosmologists particularly worked up, because the dark energy density was thought to just kind of be this, quote unquote static thing. Like it had negative pressure and it made the universe accelerate. But that's it, right? Like there was nothing else much to say about it. It just kind of is what it is. But now that thing itself is changing. Okay, so in the vacuum of space, and you can say, well, don't we have other things in the vacuum of space that are still kind of dynamic? Like, is it really, like quantum foam and stuff like this? But quantum foam still on average is a static thing, meaning, yes, it's sloshing all around the place, but it's like a boiling pot of water. Like the boiling pot of water is sloshing everywhere, but let's say the average temperature is essentially static. It's the same kind of thing. Or if you wanted to measure the up sloshes with the down sloshes, it would kind of have an average. In that sense, it's a static thing, right? That's what they were essentially saying about the dark energy density. But now it's like, no, the dark energy density itself is shifting. Okay, and that's really weird, and that's going to make it hard if that's true. We don't know yet. But if those results are true, the physics community is kind of acting like this is going to upend our understanding of a fundamental aspect of nature, a fundamental aspect of our theories of space-time. And I'm kind of here to say, yeah, not really. And the reason why I say that is because it was a stopgap to begin with. It's not like you had what would be considered in science a true explanation for the phenomenon. Using a cosmological constant or whatever you want to use, whatever variation, to say that's why, it's not a mechanism, right? The cosmological constant or just space-time density as a concept, it's not a mechanism for what causes the universe to accelerate. It's the stopgap. It's like this thing. Like what is the dark energy? I don't know. Right? Like what is it? You can show me an equation. That's not what it is. What is it? It's something we don't know. It's mysterious, right? So you can't really say it upends a fundamental understanding because you didn't really have the fundamental understanding to begin with, right? Okay, so we've got dark energy density. This new ruler comes out, right? Instead of the standard candles, it's this other approach. It's independent, corroborates a lot of it. So you already got some alignment. So that's good. Otherwise, that would be a whole other problem. But the dark energy density result is saying maybe that changes. So what does that mean, right? One more picture I kind of want to paint you conceptually about dark energy so you can kind of get some kind of anchor on it because there's not much to have because, again, it's just like a stopgap. Think of it as almost like a substance, and that's absolutely analogical. I'm using that as an analogy, so be careful. But just to anchor onto something, to sink your teeth into it, it's almost like a substance that permeates every cubic meter of the universe. And that substance, as the universe is expanding, you're kind of diluting the regular matter. So as regular matter gets more and more dilute, the constant energy density of the dark energy would be able to, quote unquote, push more and more of that matter out, right? Because it's kind of beating what gravity would have done when you have a higher density of the regular matter all squished together. If the regular matter is getting more and more dilute, but the dark energy density remains constant, you can see why that over time, the regular matter would keep expanding at an increasingly accelerating rate, at an increased acceleration, right? Because it's getting more dilute, but the energy density is the same of the dark energy. But now if dark energy is changing, it's like, well, wait a second. What was it like less in the past and then it grew? Was it more in the past and then it kind of diluted? And this is what physicists just don't really have a theory for right now. There's going to be always theories, but nothing like what and dark energy was, considered to be constant, nothing like that, right? And it kind of just throws the whole, but wait a second, how is the universe even accelerating then? If the dark energy itself, like we took that for granted, by keeping it constant, at least we could come up with that conceptual model of how the acceleration would happen, right? Regular matter dilutes, energy density stays the same. As long as the dark energy density kind of wins out in that ratio, the acceleration can be explained. But if that was less in the past or more in the past or what, right? And then it doesn't allow you to really predict the future state of the universe now. So in that sense, it throws a wrench in the gears, right? Okay, so we come to this kind of realization. We got these two kind of options here. One is that the results from the BAO, the baryon acoustic oscillation measurements, the new results that came out that are saying maybe the dark energy density itself is actually drifting, it could be real, in which case, so say the physicists, our understanding of the cosmos is going to be kind of upended, or at least this part, it's a big shift. I would say not really. You can't really make a big shift in a stopgap. I don't know if that really makes sense. I think physicists need to be a little more admitting that you didn't really know what it was to begin with. I don't know about the big shift. You didn't really have anything to shift. I'm using shift in two different ways. I got to be careful. You didn't really have anything to upend, right? The dark energy density might be shifting. I don't think that upends a lot of stuff. You didn't have much to begin with. Anyway, so either that's real, that's still interesting, the conceptual model of how the acceleration of the universe starts to change, whatever dark energy is starts to change. Maybe it's a dynamic thing. Maybe it's like a field now, whatever. The other option there is that it's an artifact. And this is what gets people really worked up now, is not everybody believes, right, that the dark energy density drift result from the BAO, the baryonic acoustic oscillation, is even real. They think there's two possibilities happening if it's not real, if it's just an artifact. One, that it's actually a consequence of p-hacking, which I'll get into in a bit, which is very, very common in science. It's a real problem with statistical analysis. And it's not something that people are doing on purpose for the most part. It's actually just a consequence of the way science is done. And you can end up showing things that look statistically significant, but actually are not. So maybe it's a p-hacking problem with the BAO data. And actually it wasn't a statistically significant drift in the dark energy density at all. So it's almost like a fake result, not faked by scientists, but just not real. Or the actual original data going back to the 1998 studies with the standard candle might actually be wrong. Maybe there was something off there. And if that's the case, we're not even talking about mishaps with statistics anymore. The actual source data that everybody uses and has been using since 98 might actually be deeply flawed. And now it's a much more kind of serious source problem, because now you got to go back to the drawing board, which won the Nobel Prize, by the way, from the 1998 studies, and say, well, wait a second, what if that's not even correct? Okay, so let's just get that kind of dichotomy broken down. You got the first branch, and then you got the branch coming off the second option. The first branch is maybe the drift really is real from the BAO. Okay, and that's kind of upends our understanding of dark energy, quote unquote understanding, not that you had much to begin with. The other option is actually just something wrong with the data itself. Either one, it's a statistical artifact from p-hacking, which I'm going to explain in a bit next, or that branches off to maybe the original 1998 data is actually wrong, and the standard candle measurements were actually nonsense. Maybe those were not nonsense, but maybe they weren't calibrated correctly. It's a systemic error as opposed to like a statistical artifact. Okay. So if it's the candle data, we got to go back, right? We got to check that out, try to figure out if that was a systemic error. I guess we're going to wait. People are going to, and there's camps, right? There's people who believe that's the problem. There's a group of people, physicists, saying they think the candle data is wrong. There's groups of physicists, cosmologists that think, no, it's a p-hacking problem. And then there's going to be that third group that thinks, no, I think maybe this drift really is real, and we have to rethink what dark energy is to begin with. Not that you really had much of an idea, right? But it's that kind of almost paradigmatic shift that's happening. Let me talk about p-hacking, because I don't know if everybody truly understands what that is. The basic idea, okay, well, let's start with p-values. Okay, so when you do a study, so let's say I want to know if jelly beans cause acne. So I'm going to go get a group of people, a sample of people who eat jelly beans, and somehow measure, I guess, acne level, whatever, on the face. And I want to know if there's a correlation, right? I want to know if that's a real association or there's just no association whatsoever. So let's say I go and I do it, and maybe my first sample I take is everybody under 40, because I don't know, younger people tend to get acne more than older people. So I go under 40, and they're jelly bean eaters, and I need to know if that association is real. The association is like a test, right? You're doing a test on the data. There's different ones you can do. Correlation would be an example. There's other ones you can do. Let's do correlation. So I want to know if people under 40 from the sample of data I took, they eat jelly beans, and do they get acne, right? Is there a correlation there? Now, how do you know, right? Because you might always get a little bit of correlation. You might not. Like, what's the level there? So in science, statistics, you come up with, specifically statistics, you come up with this kind of arbitrary value. We typically call it the alpha value, and it's usually 0.05. This might sound familiar, right? And what you want, and this is essentially arbitrary, but what that is, what the p-value is it's the probability that the data you gathered is, what is the probability that the data that you have would be at least as extreme as the data you would get if the null hypothesis is true. Now, that's kind of wordy and jargony. It's basically saying, what is the probability that you got the data that you have, let's say that under 40 stuff, right? If the opposite scenario were actually true. So usually the null hypothesis, that opposite scenario would be like there is no association, right? So it's kind of like saying, what are the odds that randomness would give you the thing that you're looking at? And you got to be a little bit careful with that definition. Some people can kind of twist that slightly and get it a bit wrong. It's not the probability that the null hypothesis is true. It's not even the probability that randomness would give you your specific result. It's more kind of casually, what is the probability that randomness or fluke would give you the result you got or greater, right? It's kind of like your result or more extreme, right? And you can get into the definitions, what does extreme mean? Kind of casually think about that based on the amount of data. Like if I have a very small sample and I get an extreme, what would look like an outlier, that's not really that extreme because I didn't have a lot of data to begin with. But if I grab a ton of data, and you can imagine, let's just say a bell curve, and the middle of that bell curve starts to tighten and tighten and tighten, right? As per the central limit theorem, we don't need to get into that. But then you would need, then if you had a really large value, that would be much more extreme because you don't expect as much variation. It kind of gets packed in the middle. But we don't need to get into all this. Don't worry. All I want you to kind of have this take-home message right now is that think of it as I grab a bunch of data and I want to make sure that whatever it is I'm looking at, like the correlation, whatever the test statistic is, that it's not randomness. because randomness can give you the same things. I need to know that it's actually a real association. Okay, so that's p-value, and we try to make that p-value, that probability, less than 0.05. Why 0.05? It's pretty arbitrary. We just want it to be low. And you can use different thresholds. You can use tighter with 0.02, right? And physicists do this as well. They typically use like a sigma as opposed to p-value, but it's the same idea. You want to make sure that what you're measuring is not just random. It's not just fluke. It's not randomness giving it to you. Okay, so that's p-values. So what is p-hacking? Okay, so I grab my under 40 data, and let's say I go to measure the value, the p-value, right? And software does this, and there's different ways it does it, but it's a basic calculation, right? It takes the variation, it takes all the things in the data, it comes up with a p-value, and let's say it gives me, like 0.20, which is definitely higher than 0.05, right? So the probability that a fluke actually gave me what I'm looking at or greater is actually kind of high. So I can't really trust that result, right? So what do I do? Well, what you're supposed to do is basically say, okay, there goes that data set. If I want to continue to do experiments, I need to go grab different data sets and try something different. But what it's kind of natural to do is say, well, I'm going to stick with the same data set, but instead of going just under 40, let's go over 40. I don't know, right? Or let's do different colors of jelly beans. Let's say I did red. Now I'm going to do a pink jelly bean. Now I'm going to do a green jelly bean. I'm going to keep slicing that same data set up and up, slicing that data up in different ways until eventually to see if I get a p-value that is actually less than 0.05. Okay, and this is sometimes called torturing the data. And the unfortunate aspect of doing science is that you can always keep torturing the same data set. Eventually, randomness is going to give what you're looking for. And that's a problem because it was given to you by randomness. It's not a real association. And the problem with p-hacking is people are basically hacking at the data, slicing it up again and again and again, right? That's one way to think of hacking, right? You're hacking the system is the other way. But the point is you keep slicing up your data until you get the p-value that says, oh, there's an association. Now, it kind of sounds like people are cheating a little bit. And in some sense, if you're very aware of this, of the human bias that's at role here, because you want to find what you're looking for, as opposed to being like, you shouldn't have a want in science. You should just be observing, but we're humans, right? And there's also this kind of branching paths problem, they sometimes call it. A natural part of science is to be like, okay, I didn't find what I'm looking for. I should just keep trying, right? So people aren't really being malicious here. They're not really trying to hack. They're like, well, maybe it wasn't right to look under 40. Maybe I should look over 40. Maybe it's just the green jelly beans that caused it. Maybe it's the red. Maybe it's the yellow. But if you keep slicing it, and the common example that is given is essentially if you slice it up 20 times, eventually 1 in 20 is going to give you the p-value less than 0.05 because the 1 in 20 is where you get the 0.05 mathematically from, right? So that's p-hacking. So back to our story about dark energy, the one camp that are saying maybe the drift from the BAO results, the new results that are coming out in the last couple of years that are saying dark energy isn't what we thought it was, maybe that's just a result of p-hacking because the BAO measurements are saying this is statistically significant, right? But maybe that statistical significance is just because you slice the same data set up again and again and you got something by fluke. You got something by random. Now, I'm not saying that's what it is. Other people are not necessarily, we don't know yet. There needs to be further investigation. And I'll talk about in a bit how scientists try to deal with this, but that's what p-hacking is, right? And if you're still wondering, but how are you supposed to get around that, right? Well, this is why you're supposed to do studies on independent data, right? When you actually do replicating studies, you don't take the exact same data set. You try to look for the same thing. I want to know if the green jelly beans are the ones actually causing the acne, but I don't take the exact same data set as that researcher. I take a different data set, a different group of people, right? I don't know, maybe different jelly beans, whatever. Maybe you want to keep that the same, but something is different about it, and you independently see if you get the association. You don't keep slicing the same data up again and again. And so people are going back to these new BAO measurements and how they were done, and they're trying to figure out if it's a result of p-hacking or if it's actually the 1998 Standard Candle data that was wrong and the BAO, which still in some sense even though the physics is different, it still relies. It connects to some of the cataloging that was done in the original 98 studies. Okay, so that's kind of where we're at, and that's why, and it's interesting, and it's going to be interesting to see how this plays out, right? Is it a statistical artifact from p-hacking? Is it kind of is it not even a statistical artifact, but something from the original 98 data? Or is it real? Is the dark energy density, whatever that is is it actually drifting, right? My point in this episode is I think the kind of whole hoopla around it is a little bit goofy because I think we're forgetting, and this is what happens in science, that this was actually kind of a placeholder to begin with. I get that there's real science there. I know there's real redshift measurements and standard candle measurements. And yes, the universe is not only expanding, but accelerating. But why? Like, what's the mechanism? Let's be honest, we don't have that. Calling it dark energy is the admission right there. What is dark energy? What does that even mean, right? So it's kind of like, it's not really that upending in my opinion, because you didn't have much to upend to begin with. Let's use some other examples in science just to be clear of what I mean by stopgap, right? Where you kind of do bookkeeping and then something's missing and then you kind of just say, maybe that's what this is, but you don't really have the theory, right? So dark matter is the closest cousin here. Again, you're looking at let's say the rotation of the galaxies, and the speed is not what you would expect it to be, because that speed would be essentially be dictated by the gravity. The gravity is dictated by the amount of mass that you have, but given the amount of regular mass that's there, that doesn't explain it, so there must be missing mass. Real science, all real measurements, yes, but what is the mechanism causing it to spin faster? Let's call it dark matter. Like, there's missing mass, so from a bookkeeping perspective, we'll just add more matter and call it dark matter. And some physicists might push back a bit, like, you're kind of downplaying it, you're simplifying it too much. Yeah, but it's still a stopgap, right? Again, it's right in the name, we don't really know. It's kind of funny, actually, right? So that's not really a mechanism, right? We know the mechanism is mass that makes the rotation. You just can't account for all the mass that's supposed to be there. So you just say, maybe there's more, we'll call it dark. We don't know where it comes from. Inflation is kind of like this, right? You can look at things like CMB. You can take a look at the density. Well, more to the point, you can kind of look around the whole universe and you can say, things are really the same and you might not expect it to be. Like, it's very isotropic as opposed to anisotropic. Like, isotropic means like maybe the temperature over on this side of the universe is the same as the one over here. Like, how is it so uniform? And so I think it was in the 70s, right? Alan Guth and all that. You get this kind of inflation that happens super, super fast. And it kind of, I guess, homogenizes the density. And then from that point, it starts expanding. And maybe that's why it's uniform. Again, we don't need to get into all, it's beyond the scope of this episode, but that's kind of a stopgap as well. It's like, well, yeah, what is that? Like, why would that even happen? And it's not just me, right? Like, you get people pushing back on these theories because they're stopgaps, right? Even wave function collapse. I mean, quantum mechanics is super counterintuitive. The whole thing is like statistical in nature. We don't really know if that means reality is statistical at a foundational level, or it's just because there's missing variables or something more foundational we don't have access to. That's what Einstein thought, right? In many ways. So wave function collapse is kind of a stopgap in a way. Again, tons of math, arguably the most scientifically validated theory of all time. So it's kind of weird that would be on a stopgap. But in terms of the underlying mechanism, like, what is the actual wave function? We don't know. We have interpretations. We've got Copenhagen interpretation. We've got many worlds interpretations. We've got all this stuff, but we don't know, right? And it's not just that you always don't know in science because a theory is never complete. That's not really what I'm talking about. Like, yeah, epistemically, that's true. It's beyond that. It's not even much of a theory at all, actually. Quantum mechanics is, but the wave function itself, super, super controversial because it does have this stopgap aspect to it. Some of the quantum foam stuff, 0-point energy can almost be in there. Even entropy, actually, which is, we talk about entropy all the time, but what is it really, right? Like, you can measure it very exactly, but is it like related to the illusion of time? Is it just disorder? People push back on that a lot. Now, it's not really disorder, right? It's how let's say the number of configurations map to the macro state. It's not just the usual uncertainty. There's a little bit of stopgappiness in it. Fitness in biology, right? Fitness landscape specifically, it's actually kind of circular. Like, a thing survives because it's fit. That makes sense. Why is it fit? Because it survived. Why did it survive? Because it's fit. Why did it fit? Because it survived. You get into this kind of circularity here. It's a little bit stopgappy. Intelligence is probably the best example, especially related to IQ. A lot of stupid stuff here. Just really, this is definitely the worst case scenario, I would argue. Particularly, particularly when you talk about the G factor, you do what is effectively this kind of high dimensional form of linear regression. You do basically a PCA on it. I'm not going to get into it, but you basically find this vector pointing in a certain direction in high dimensions, but that's fine. And you can say, okay, that's the correlation. Okay, that's fine. But then you point to the correlation vector and you say, that's actually what intelligence is. It's like, whoa, what? That's actually what intelligence is. And there's people that believe that, like, they reify which means to bring something very abstract into reality, this G factor, and say maybe that's actually what intelligence is. Total stopgappy, total, yeah, in other words, you don't know, and you're pointing at this drastically oversimplified version of statistics and saying that's actually what intelligence is. It's a really bad version. Consciousness is maybe the best example, right? The hard problem, like what is consciousness? We all believe it's a thing, because I don't know, I'm self-aware, I seem conscious, I know who I am, I think I know who you are, I believe that you also have consciousness. Right, we kind of get a sense, but it's very kind of ill-defined, right? It's almost stopgappy. Like, I think a good example of this is when people try to say, well, AI can't be conscious. Well, what does that mean? If we don't even really know what consciousness is, so how do you know that AI cannot have it? It gets kind of goofy, right? Even genes actually started like this, although historically anyways. The idea of a gene was essentially an abstract mathematical construct, which was used as a stopgap to basically help explain the heritability that was seen in observations that people believed existed. And then eventually now, with modern genetics and all this kind of stuff, we can kind of pretty much point at it and say, yeah, we're pretty sure there's this thing called a gene there. And obviously DNA gives you the substrate for all this kind of stuff. So that's not so much like still a stopgap, but that is how it started. So stopgaps are not always bad. Like maybe there really is a wave function. It's part of physical reality, right? Maybe inflation is exactly right. Maybe dark matter, maybe dark energy really is a thing. And it's not just, maybe it's okay to use it as a stopgap right now because it's allowing science to continue and that's what we need. But it's not where genes are, right? Recognize it as a stopgap, right? Anyways, there's other examples in science. Well, the cosmological constant, right? And Einstein's quote unquote greatest blunder kind of thing, right? So yeah, stopgaps are normal, and I'm not saying don't use them. I just want laymen, first and foremost, to understand, that there are a lot of stopgaps like that in science, and they're not as foundational as it might seem. And scientists need to do this too, because what originally starts as a stopgap starts being folded into the paradigm of science, and then it starts being taken almost as a fact. And we know this because this is a perfect example with dark energy. The way that the physicists and cosmologists a lot of them are reacting, like this is this amazing result that all of a sudden the dark energy density is shifting, and it's almost like a paradigm shift or something. It's upending our understanding. No, not really. You didn't really have a lot of understanding to begin with. Let's go back to what the 98 studies and the discovery by subtraction was actually doing. Let's admit what dark energy is, which is a stopgap. It's not much of a theory to begin with. It's not super upending. Maybe it's not really that surprising that it's not constant because you didn't have the it to begin with, really. You see what I'm saying? I'm pushing back on that, and I think this is kind of reflective that things get folded into the paradigm, and then all of a sudden we think it's fact. But when you say it's fact, you say, yeah, but what is it? And science should be able to have an underlying mechanism of some sort to explain that, right? Anyway, I think that's all I want to say in this episode. So it's big results coming in, big results. And a lot of people are almost pivoting careers over this stuff, and it's getting a lot of buzz. And as I do in Science in Perspective, I just kind of want to de-hype it a little bit. Let's not forget what we're talking about here, this stopgap thing that we had for a few decades. And then when we found out the universe was accelerating, we're like, yeah, maybe that's what that is. Maybe. So but it'll be interesting to see. Are the BAO measurements, the baryon acoustic oscillation measurements, is that really saying something about this thing we call dark energy? Is it actually drifting, or is it a statistical artifact? And by the way, that p-hacking, it happens in medicine all the time. You could almost say half of biology. I'm exaggerating a little bit, but not much. I mean, it's super, super common, right? Sociology. Doesn't happen as much in physics, which is why it's kind of interesting to hear the p-hacking in physics. Just because they're not going to rely on statistics anywhere near as much as something like sociology, right? Not in that way anyway. So it'll be interesting to see how that is. And there's things you can do, right? Like you can pre-register. You basically have to, as a good scientist, to avoid p-hacking, you should be saying, here's the data set I used. Pre-registering basically means here's the hypothesis I essentially designed from the beginning and then I didn't change it. Or if I did, here's the lineage of it. Right, you should be using multiple data sets. You should have other groups replicate it if and when they can by using different data. You should announce, basically what you're doing with your data and how you did it, and keep track of it. And there's kind of reporting on confidence intervals and all this kind of stuff. You can kind of do the extra stuff. and replication. It gets into all that stuff. But I would, that's kind of the usual remedy to p-hacking. But I think it's like, let's just step back and admit what this is. I don't think it's that particularly groundbreaking. It might prove to be, but we're still talking about a stopgap. We're not talking, I would barely call dark energy a real theory. And I'm not the only one who thinks that. I think a lot of people kind of push back on that. It could still be real, right? And we don't know if the new measurements are anything different, but let's just admit what it is and be aware of that when you hear things in science, right? Dark energy is a thing that all the theoretical physicists truly understand. No, they don't. Or if you hear something and you don't know, maybe ask a scientist. It's just like, do you have a mechanism? Or is this kind of just a stopgap for now because you don't really know? It's very pervasive in science. And it's just important to know that that's not, that is the case. Okay. Anyways, that's it for this episode. And thanks everyone for listening. And for those of you who are watching, go ahead and check out dekyon.io, dekyon.io. Go ahead and become a member on there for $9.99 a month. And you can learn all kinds of stuff about science related to the things that I'm talking about. You can dig deeper. You can ask AI. You can find connections across episodes. You can ask about techniques based on what I've talked about if it relates to your life or investing. Science can be super, super useful, or how to spot things like this a little bit better, whatever it is. Become a more effective person as such. There's a forum on there for conversations. That's where the community is talking. Data visualizations to see how concepts are related. A study space you can use to kind of both test yourself a little bit, but even just to dig into the material deeper and more effectively. Go ahead and continue your journey of being someone, whether you're a layman or an expert or something in between. Continue your understanding of the science that's making the headlines. Okay, thanks everyone. Until next time, take care.